Welcome back. Today we're going to discuss Section 3.2, Understanding and Interpreting Confidence Intervals. I've broken this section into two different pieces. So the first subsection is confidence intervals, just getting comfortable with what a confidence interval is. And then we'll work on confidence intervals in context. We're going to learn how to talk about confidence intervals within the context of some specific problems. So let's begin our discussion with confidence intervals. And let's begin our discussion of confidence intervals with a little review problem. This will remind us of how we use the terms parameter and statistic correctly. Now, we'll work this out in some detail using the overhead camera, but let's read through the problem right now. In each case, identify the population and the parameter of interest. What statistic would you use to infer the value of the parameter? So question 1, what is the average height of a male student at Furman University? Question 2, what proportion of the voting age residents in South Carolina will vote for Bernie Sanders in the primary? And question 3, what is the correlation between BMI and waist circumference in adult males in the United States of America? Meet me at the overhead camera. We'll work these problems out in detail. So I'll see you over there. All right, so the first question asks us, what is the average height of a male student at Furman University? And remember, we're going to try to identify the implied population, the implied parameter of interest, and then we're asked to identify the statistic we would use to infer the value of the parameter. So what is the average height of a male student at Furman University? So the implied population, it seems to me, is the population of male students at Furman University. So we're going to say that the population consists of all male students at good old Furman University. All right. The parameter of interest to us, though, is the average height. So we're going to call that, since it's an average height, we'll call that a mu, a mean. We'll say that this is the mean height of the population. Okay? What statistic would we use to estimate this? Well, we'd pull a sample out of that population, and we would calculate X bar, which is what? The mean height of the sample. Okay? So we've got a population of male students at Furman. Mu is the mean height of that population, and X bar is the mean height of the corresponding sample. All right, what proportion of the voting age residents in South Carolina will vote for Bernie Sanders in the primary? So our population, we're thinking of the population as voting age residents in South Carolina. The parameter of interest to us in this case is the proportion. So we're going to call that P. This is the proportion of the population that will vote for Bernie Sanders in the upcoming election. What statistic would we use? Well, if we were able to sample from the voting age residents in South Carolina, we would compute the corresponding P hat, which, if I had space, I would write it as the proportion of the sample that will vote for Bernie Sanders. Okay, so it's essentially the same language, except I would replace population by sample. That's the only change I would have to make. Otherwise, I could read it exactly the same way I read this one. Okay? What is the correlation between BMI and waist circumference in adult males in the United States of America? So the population is the adult males in the U.S. Now we're looking for a correlation in this case, and so within a population we would use the Greek letter rho for that. So this is the correlation between these two quantitative variables, correlation between BMI and waist circumference in the population. And we know that when we pull a sample out of this population and compute the correlation, we would identify that because it's coming from a sample, we would identify that with R. So this is going to be the correlation between BMI and waist circumference in the sample. Okay, so the big difference here is that in each case we identify a population, and within the population we would have a parameter that's notated one way and a statistic, because it's associated with a sample, that would be notated in a different way. But these are tuned to each other, so according to a mu we would have an X bar, for a P we would have a P hat, and for a correlation rho we would have a sample correlation or an R. Okay, so that's just kind of by way of review. Let's go back to the class notes. Beginning here in Chapter 3, but throughout the rest of the course, we will be studying inferential methods in statistics. An inferential method, if you remember, is trying to say something intelligent about a population based on what we're observing or witnessing within a sample. And there are two basic inferential methods that we'll be studying in this course. One is confidence intervals, and the other one is hypothesis testing. And really, these tools are being used to answer very different types of questions. So let's take a look at a question that is answerable by a confidence interval. So the question might be, what proportion of likely voters will vote for X, where X could be a candidate or some proposition? All right. Now, what is this question asking us to do? It's asking us to locate a parameter, right? The proportion of likely voters that will vote for X. It's asking us to tell me something about the value of that proportion. Now, what a confidence interval does is it locates it within an interval. There's a lower bound and an upper bound for the location of that parameter. Now, that's never done with absolute certainty. It's done with a certain level of confidence. All right, so that is what a confidence interval is helping us do. It is helping us locate a parameter. By contrast, let's take a look at a question that seems appropriate for hypothesis testing. Which is the safer cap color for hunters, blaze orange or yellow? Let's say you work for a company that's been manufacturing hunting caps, and what is the virtue of a hunting cap? We want it to be visible so that hunters can see each other when they're out in the woods. And so let's say you've been manufacturing them in yellow for a number of years, but now you're interested in knowing if, in fact, blaze orange gives more protection. So you'd want to conduct some kind of statistical test. You might invite a group of volunteers, randomly selected, let's say, into a space. And let's say you set up the following experiment. You let them view a wilderness scene for a set period of time. And within that wilderness scene, there's a yellow cap and there's an orange cap. And at the end of the experiment, you ask them, did you see the yellow cap? Did you see the blaze orange cap? And really, their answers can be one of four cases, right? They may not have seen either cap, and I'll put you in this region of the Venn diagram. They may have seen both caps, and that would put you into this intersection in the Venn diagram. But the slices or the pieces of this Venn diagram that are most interesting to us are the people that saw blaze orange only and the people that saw yellow only. Those are the people that will help us discriminate between the blaze orange or the yellow as the more safe color, let's say. All right, now how does this become a statistical question? Well, let's say the number of people that saw the blaze orange is just slightly bigger than the number of people that saw yellow. We might come to the conclusion that there's not strong evidence that orange is better than yellow. If there's a lot more people, many more people that saw blaze orange than yellow, now we might come to the conclusion that the blaze orange is better than yellow. And what statistics is going to allow us to do is sort out where that threshold has been crossed. When is the evidence for blaze orange over yellow so strong that we feel compelled to agree with the claim that blaze orange is better than yellow? So that is a typical question that is answered through hypothesis testing, and that'll be something that we'll talk about later in the course. But for now, understand that confidence intervals fits into one of the two inferential methods that we will be studying in this course. So we're really interested right now in locating a parameter in an interval. So that'll be our task. Now, it is very likely that you've actually seen some confidence intervals either in the newspaper or on the internet. Let's take a look at confidence intervals in the media. On July 24th, 2020, Rasmussen Reports estimated that 37% of likely voters strongly approve of the job President Trump is doing. Later in the article, they write, and I want to draw your attention here to the yellow highlighted bit, the margin of sampling error for the full sample of 1,500 likely voters is plus or minus 2.5 percentage points with a 95% level of confidence. Now, on the next slide, I want us to try to unpack the meaning behind all of this verbiage. Let P be the proportion of likely voters in the population who strongly approve of the job that President Trump is doing. Let P hat be the proportion of likely voters in the sample who strongly approve of the job that President Trump is doing. Now, we are told that P hat is equal to 0.37. In other words, 37% of those sampled strongly approve of the job that President Trump is doing. Now, we would like to believe that that 0.37 is reflective of the value of P within the population. Now, here's how Rasmussen articulates their claim. The claim is that P is equal to 0.37 plus or minus 0.025. That's the margin of error, right? So they're saying if I take the 0.37 and I subtract 0.025, and if I take the 0.37 and I add 0.025, that locates P in an interval between 0.345 and 0.395. Now, in fact, Rasmussen Reports is not even claiming that P necessarily has to land in that interval. They're just saying we have a lot of confidence in our methods. We are 95% confident that P will land in this interval. So this article is giving a 95% confidence level. This means that Rasmussen Reports has a 95% confidence that the interval from 0.345 to 0.395 contains the population parameter P. Let's take a look at the technical definition of a confidence interval. A confidence interval for a parameter is an interval computed from sample data by a method that will capture or cover the parameter for a specified proportion of all samples. So the thing to understand about a confidence interval is that each sample is going to produce a slightly different confidence interval. Some of those confidence intervals will cover or contain the parameter of interest, and some of them will not. So the success rate, the proportion of all samples whose intervals contain the parameter, is known as the confidence level. Now let's talk about how we construct or compute confidence intervals. So if we can estimate the standard error, SE, and if the sampling distribution is relatively symmetric and bell-shaped, a 95% confidence interval can be estimated using statistic plus or minus 2 times SE. Now, 2 times SE is just what's called the margin of error. So we take our sample statistic and we tack on plus or minus the margin of error, which is calculated as 2 times the standard error. Now, equivalently, just using different terminology, we can say that the confidence interval is our best estimate for the parameter of interest plus or minus 2 times SE. So I think it's incredibly helpful to have a geometric picture or a geometric understanding of a confidence interval. So let me offer you the following picture. right? We have a confidence interval here pictured in red. Now, the center of that confidence interval is obtained by our best estimate, right? We're trying to estimate a parameter. We calculate a statistic within the sample, and that forms our best estimate, and that gives us the center of our confidence interval. The radius of the confidence interval, in other words, the distance from the center to each of the two endpoints, is our margin of error, or 2 times the standard error. So if we take SE multiplied by 2, that's giving us the radius of our confidence interval. Now, the thing to understand is that 2 times SE is not going to change from sample to sample. What does change, though, is our best estimate. If we resample, we will find that our best estimate may change slightly. Now, that has the effect of sliding our confidence interval to the right or to the left as the value of our best estimate changes. The width of our confidence interval, which is obtained by multiplying 2 times the standard error, is not going to change. So we should imagine these confidence intervals as intervals of more or less equal width or equal length, but whose centers are changing according to the particular sample that we've drawn from the population. Now let's think of all the different things that influence a confidence interval. So remember, our confidence interval is of the form best estimate plus or minus a margin of error, which is calculated by taking 2 times the standard error. I want us to think of a confidence interval as being influenced by 3 different things, which I have labeled 1, 2, and 3. So 1 is related to the best estimate. The best estimate is determined by the particular sample you draw. Different samples will produce different values for the best estimate. So that's the influence that a particular sample has on our confidence interval. It is going to determine the center of that interval. Now, let's look at this number 2. The number 2 is really an artifact of our 95% confidence level. We will see later that each confidence level has its own unique multiplier. So this number 2 that sits in front of the SE is going to be changeable. As we change our confidence level, that multiplier will change accordingly. Finally, let's look at the influence on this third part, the standard error. That standard error is influenced by the size of the sample and the natural variation of the quality or quantity of interest within the population. So part of the standard error is made up by something that we cannot control, and that is what's happening in the population itself, the natural variation of that parameter within the population. The one thing that we can control is the size of our sample. So by changing the size of our sample, we can influence the value of the standard error, and therefore we can influence the margin of error. All right, so the things that influence a confidence interval are best estimate, that gives us the center, our level of confidence, that gives us our multiplier, and the sample size, which gives us part of the value of SE. Now, I want to work some problems with you where we practice using the best estimate plus or minus 2 times SE formula to construct some confidence intervals. So in 2013, the citizens of Maryland voted on a referendum question 6, labeled RQ6 for short. Suppose a sample of size 100 is collected from the population. Let's let P denote the proportion of the population that favor RQ6, and let P hat denote the proportion of the sample that favor RQ6. Now, the standard error of the sampling distribution of P hat, SE, is equal to 0.049. In each case, find a 95% confidence interval for P corresponding to the stated value of P hat. The true value of P is 0.52. Which intervals cover the true proportion? And so you can see we've got a variety of different values for P hat. Each value of P hat is going to give us a slightly different confidence interval. Some of those will cover the 0.52 and some of them will not. Let's go to the overhead camera and work this problem out in detail and see the exciting results. Welcome. So in this case, in each case, we're going to find the 95% confidence interval for the parameter corresponding to a stated value for p hat, and all we have to do is remember that the standard error associated with this sampling distribution is 0.049. So here's the essential calculation, and this is going to be a recurring calculation throughout. The margin of error, let's just compute that here because it'll be the same throughout. The margin of error is going to be 2 times 0.049, which is going to be 0.098. So in all of our calculations, we'll be adding the margin of error and subtracting the margin of error accordingly. Okay, so in this first problem, we want to calculate our confidence interval. So we're going to take 0.55 minus the margin of error and 0.55 plus the margin of error, and those will form our two endpoints. This first calculation gives us 0.452, and the second calculation gives us 0.648. So our interval extends from 0.452 out to 0.648. Now, one of the questions we're always interested in is we know the true parameter in this case is this 0.52, and so the question is, did we cover that parameter with this interval? And in this case, we would say yes, this covered. We got coverage. Okay? Now let's redo this calculation with 0.4 in place of the 0.55. Okay? So all we have to do is change up our calculation a little bit, and we can get our new confidence interval. So now we're just going to use 0.4 minus 0.098 and 0.4 plus 0.098. This is going to give us two values. One is going to be 0.302, and the other endpoint is going to be 0.498. Our corresponding confidence interval will extend between those two, from the smaller to the larger, of course. And in this case, we see that our parameter of interest, the 0.52, is not covered. And so this would be a no. Okay? Our sample ended up so far to the left, right, that it ended up producing an interval that didn't cover the parameter of interest. Okay, now if we change out the 0.4 to 0.47, we're going to see a corresponding change in our interval. So now it's going to go from 0.47 minus, we'll do the minus case first, 0.098. So we're first subtracting, and then we'll add. So this is 0.372 up to 0.568. So our interval extends from 372 to 568. And in this case, we do see that we did cover the parameter of interest. In our final calculation, we're going to pick a p hat that ended up pretty far to the right. So it'll be interesting to see when we change up our calculations what happens in this case. So now our confidence interval is going to go from 0.66 minus 0.098 to 0.66 plus 0.098. And here we'll see a change in values. We'll have our left endpoint at 0.562 and our right endpoint at 0.758. So we'll be going from 562 to 758. And now we can see that because our p hat was so far to the right, it dragged the confidence interval over and it no longer covers. So this one is a no. It does not cover. All right, so hopefully this gives you some sense as to how we could take some information about the sample proportion in this case and the margin of error and put those together to produce the confidence interval, and notice in each of these cases whether or not it did cover the parameter. Okay, let's go back to the class notes. All right, so welcome back. We're now going to try to simulate the Maryland RQ6 problem. So we can simulate samples and confidence intervals for the Maryland RQ6 question. We're going to load StatKey, go to Sampling Distributions, Proportion, click Edit Proportion, and set it to 0.52. So in other words, we're creating a population in which the proportion of people that favor RQ6 is set at 0.52. Now, we're going to click Choose Samples of Size n equals 100, and then we're going to click on the Confidence Intervals tab. Now, what that's going to allow us to see is that every time we draw a sample of size 100 from that population, we're going to see a value for p hat appearing, and we're also going to see the corresponding confidence interval appearing. So we're going to generate some samples and watch the corresponding confidence intervals, and then we're going to ask what fraction of the confidence intervals generated cover or capture the true proportion. So we're going to StatKey, Sampling Distributions, Proportion, and we don't care what the default file is because we're going to be doing some editing. We're going to edit the proportion. We're going to put in the 0.52 that we think accurately reflects the true proportion of voters in Maryland and their feelings about RQ6. So we believe that 52% of the population is in favor of that referendum. So we'll put that in there. And also we're working with samples of size 100, so we'll edit that. Now, when we generate a sample, what are we doing? We're imagining reaching into the population of Maryland, pulling out 100 citizens, finding out how they feel about referendum Q6. In this case, in this particular sample, we got 54 in favor, and that gives us a p hat of 0.54, and then that dot is dropped into this main display here. So we can generate one sample at a time, or we can generate them 10 at a time. But the point is we're now up to 43 samples, and each one of those represents a different time that we reached into the population to draw out a sample of size 100 and query that population and calculate the corresponding value of p hat. Now, what we're really interested in, what's really new here, is to look at this confidence intervals tab. Let me show you what that looks like. So when we click on that tab, what this is going to show us is the confidence interval that's associated with each p hat that we've calculated. So let me show this to you. I'm going to have to ask you to look over here to the right after I mouse over one of the dots in our dot plot. So when I mouse over this particular dot, you can see that that sample is highlighted. So that was one of our samples. That was one of our p hats. And over on the right, when you look in the confidence intervals display, you can see the confidence interval that is being highlighted. That is the confidence interval that is associated with that particular sample. Let me pick another one just so you can kind of see the variety of samples and their corresponding confidence intervals. There's another sample that I'm highlighting, and you can see the corresponding confidence interval in the confidence intervals display. Now, let me show you what the red ones correspond to. When I pick one of these samples that's far off to the right, you can see that the corresponding confidence interval is off to the right, and it's colored red. It's colored red because it is so far off to the right that even after I fatten it up with that margin of error, it's not wide enough to cover the true proportion. It's not wide enough to cover 0.52. Now, in this display, the 0.52 is represented by this vertical bar. So any interval that is crossing that vertical bar is covering the true proportion of 0.52. So this one out here is so far off to the right that even after we throw on the margin of error, it's still not wide enough to cover the true proportion. And this one over here is so far off to the left that even after I tack on the margin of error, it can't cover the true proportion either. All right, let's generate several hundred samples and take a look at the corresponding confidence intervals. Now, I know it gets very densely packed over here, so it's very hard to make sense of what's going on here. But after I generate several hundred examples, what we're seeing over here is that most of the intervals are colored green. In other words, most of the time we are generating a sample such that when I fatten it up with the margin of error, it's going to cover the true proportion of 0.52. Every now and then we hit one that is so extreme, so far off to the right or so far off to the left that the fattening of that sample point doesn't allow us to get coverage or containment of the true parameter. All right, now if we look up here under coverage, we get a very important statistic, right? It says we've generated 443 samples, and of those, 418 of the corresponding confidence intervals successfully captured the parameter, and the remaining did not. In other words, we're getting a success rate of 94.357%. Now, this is the meaning of the 95% confidence, right? It's saying 95% of the time, or roughly 95% of the time, we're expecting to be successful with this procedure. Every now and then, we pick out a sample that is so far to the right or so far to the left that our procedure fails us. But most of the time, this is going to work. Now, one way to think about this to try to start connecting all of the dots here, no pun intended, is if we think about what's going on here, when we are selecting dots that are so far out to the right or so far out to the left, in other words, in the upper 2.5% of the dot plot or the lower 2.5% of the dot plot, those points are so far removed from the center that their corresponding confidence intervals will not cover. So the 95% confidence level is really connected back to our middle 95% of the dot plot. The dots that are close to the center in the middle 95 will have corresponding green confidence intervals, ones that cover, and the ones that are in red out here will have confidence intervals that will not cover. Okay, so hopefully that's bringing all of this together, and hopefully that is making sense for you. Now what I want to do is return to the notes and work out another problem using our formula best estimate plus 2 times SE. So let's work on that idea again. What is the true correlation, rho, between the levels of pH and the mercury in the lakes of Florida? Samples are collected from 53 randomly selected lakes in Florida. The standard error in the sampling distribution of R is 0.084. For a sample correlation of R equals negative 0.575, give the corresponding 95% confidence interval for rho. So we're going to go off and work this problem under the document camera, so join me over there to see the solution to this problem. Okay, so let's work out the details for finding this confidence interval. Now remember, we've got our sample correlation is negative 0.575. That's going to form the center of our confidence interval. We know that the standard error for the sampling distribution is 0.084, so that'll become part of the margin of error calculation. So the two endpoints for our confidence interval are going to be obtained by taking the negative 0.575 and subtracting 2 times the standard error, and negative 0.575 plus 2 times the standard error. Remember, 2 times the standard error is just the margin of error. And these calculations, we can do these calculations relatively easily. When I take negative 0.575 and subtract 2 times 0.804, I get negative 0.743. And when I add 2 times the standard error, I'm going to get negative 0.407. So our confidence interval is simply going to be what I get when I go from negative, the smaller, negative 0.743, up to the larger, negative 0.407. Okay, and how should we think about this? We are 95% confident that this interval is going to cover the true value of rho. Whatever that true value of rho is, we believe that this interval is going to cover that. We have 95% confidence in our method. Okay, so let's go back to the course notes, and I'll see you over there. Who exercises more, men or women? A survey of 20 men and 20 women is to be conducted. We're going to let mu sub m and mu sub w denote the mean number of hours of exercise per week for the men and for the women within the population. We're going to let x sub m bar and x sub w bar denote the mean number of hours of exercise per week for the men and for the women within the samples. The standard error in the sampling distribution of x sub m bar minus x sub w bar is 2.33. Now a sample is collected and it is found that x sub m bar is equal to 12.4 hours per week and x sub w bar is equal to 9.4 hours per week. In other words, for the men that were selected, they exercised on average 12.4 hours per week, and for the women selected, we found that they averaged 9.4 hours per week. So certainly within the samples, we are seeing a difference in the number of hours exercised per week. But now we want to build a confidence interval for the true difference in the proportions, the true difference in means. So, based on this sample, find a 95% confidence interval for mu sub m minus mu sub w, and then we'll ask a follow-up question. Is there enough evidence to suggest that mu sub m minus mu sub w is positive? Let's work out the details to this problem. Now, the first thing we need to figure out is what is the center of our confidence interval? We're trying to locate this parameter mu sub m, the mean exercise hours for men, minus the mean exercise hours for women, mu sub w. Our best estimate for that is going to be what we get from the sample, where we take those differences in exactly the same direction. So we should take x bar sub m minus x bar sub w. That's going to be 12.4 minus 9.4, and that's going to be 3. So our best estimate for this difference is going to be what we're seeing in the sample, which is going to be 3. We think that there is 3 hours of difference. That's our best estimate from the sample. Now, in order to compute the confidence interval, though, we have to add and subtract 2 times the standard error for that sampling distribution. And so we're simply going to have to take that 3 and subtract 2 times 2.33, and then take that 3 and add 2 times 2.33. So we'll have 3. One of our calculations will be 3 minus 2 times 2.33. And one of our calculations will be 3 times 2 plus 2 times 2.33. So these are the essential calculations that we have to carry out. Now, when you do this, when you take 3 minus 2 times 2.33, you're going to get negative 1.66. And when you do the calculation 3 plus 2 times 0.233, you're going to get 7.66. So we're 95% confident, right, that the true value of that difference is somewhere between, right, it's a fairly big gap here, somewhere between negative 1.66 and 7.66. Okay? All right. So that helps us locate the parameter. We have pretty high confidence that the true value of this difference is inside this interval. Now, is there enough evidence to suggest that this difference is strictly positive? Now, given that our interval contains both negative numbers and both positive numbers, we really can't draw this conclusion out from this evidence, right? All we know is that we have a lot of confidence that this difference sits inside this interval. So for all we know, this difference could in fact be less than 0, it could be equal to 0, or it could be positive. Any one of those 3 things is possible based on what we're seeing here with this confidence interval. Now, if this confidence interval consisted only of positive values, for instance, if it extended from 2 to 4, Then we're saying we have 95% confidence that this difference is between 2 and 4, which would force it to be, of course, positive. But we don't have that situation in this example, so I would say no, there is not enough evidence to draw this extra conclusion out of what we're seeing in our confidence interval. Okay, that concludes the solution to this problem, so let's go back to the course notes and continue. I want to close section 3.2 just by talking to you a little bit about confidence intervals in context. When speaking or writing about a confidence interval, you should make the interval the subject and the parameter the object of the sentence. In other words, you should think of the interval as the thing that's acting in the sentence and the parameter the thing that is receiving the action. I think if you begin to articulate your results this way, it will help you understand the process better. So this is all about understanding the underlying process. Okay, here's a good way to articulate a result. We are 95% confident that the interval from A to B contains the parameter. Here's another good way to articulate your result. We are 95% confident that the interval from A to B covers the parameter. Now here's an articulation that I don't think would cause too much confusion, especially if you know what's going on, but it does, I think, paint the wrong picture. I think it should be avoided as a result. So there is a 95% chance that the parameter is in the interval from A to B. Now, the reason I don't like this articulation is it appears as if the parameter is changing, as if the parameter has a chance of being in the interval or does not, because it's kind of moving around. It's active. In fact, it is not. It is a fixed quantity that you are trying to capture with your confidence interval. So think of the parameter as fixed. It is passive. It's the interval that's active. It's changing from sample to sample. And the question is, does this sample produce a confidence interval that covers that parameter or not? Okay, now, so again, I don't think anybody would be too terribly confused if the result was announced in this third way. People who know what's going on would be able to understand that and make sense of it. But at this point in your career, I think it's really, really beneficial for you to try to articulate the results in these good ways and try to avoid this third articulation. Okay, enough about that. Let's go work a problem and practice articulating our results. A random sample of 1,483 U.S. adults were asked, is a car a necessity or a luxury? The sample proportion of those who said that a car is a necessity is p hat equals 0.86, and the SE of the sampling distribution is 0.001. First, find the 95% confidence interval for P, the true proportion of U.S. adults who think that a car is a necessity, and 2, explain the meaning of this confidence interval in context. Now, this is mostly an exercise in explaining the meaning of this confidence interval in context. So I've taken the liberties of having the Desmos scientific calculator do the work for us of computing the endpoints of this confidence interval. So when we take the p hat and add 2 times SE, we get the upper limit of 0.862. And when we take 0.86 minus 2 times SE, we get the lower limit of 0.858. So we now have a confidence interval extending from 0.858 to 0.862. Now, what is the meaning of that interval? All right, here's one stab at this, right? We are 95% confident that the interval from 0.858 to 0.862 contains the proportion of U.S. adults for whom a car is a necessity. Or, we are 95% confident that the interval from 0.858 to 0.862 covers the true proportion of U.S. adults for whom a car is a necessity. Okay, so both of those would be fine. We would be happy with articulating our result in that way. Okay, one last thing I want to cover. In each case, what effect will the change have on the width of the confidence interval? So I want us to think about this, right? Change number 1, we lower our confidence from 95% to 90%. So now we're interested in building a 90% confidence interval instead of a 95% confidence interval. The question is, what is the effect that this will have on the width of the confidence interval? Will the interval be wider or will it be narrower? Okay. Now change number 2 I want us to think about, right? What effect will this have on the width of the confidence interval? We work with a larger sample. So to put it another way, if I work with a larger sample, do I expect the width of the confidence interval to increase or decrease? So let's think about each of those questions a little bit, and let's see if we can articulate some answers. Okay, let's think about situation 1. We lower our level of confidence from 95% to 90%. Now, I hope you've come to the conclusion that this should have the effect of making the confidence interval narrower. And one way to think about this is to think about the parameter of interest is it's like a fish out in the water ahead of you. And on shore you have 2 different nets to work with. One is a bigger net and one is a smaller net. Obviously, you have more confidence in catching that fish with the bigger net than you do with the smaller net. And in a way, a confidence interval is just like a net, trying to catch that parameter. You're going to have greater confidence in a wider interval and less confidence in a narrower interval. So just remember this, right? As you take your confidence level and make it go from 95 to 90%, your confidence interval is going to have to also shrink. It's going to have to become narrower. All right? Now let's think about situation 2. What will be the effect on the width of the confidence interval by using a larger sample? Well, let's think about this. When you use a larger sample, you are collecting more information about the population parameter of interest. You are, in fact, making the standard error smaller. Okay? Now, the standard error, 2 times the standard error, is the margin of error, and that's the radius of your confidence interval. So using a larger sample decreases the standard error, decreases the margin of error, and ultimately makes your confidence interval narrower. Okay, so that brings an end to section 3.2. I hope you've learned something about what a confidence interval is, how to compute it, and how to talk about it intelligently. I will see you again for another video lecture on section 3.3. Until then, take care of yourself.